the actual wave parameters that you define, or you can define from the wave spectrum. And really, these are the kind of parameters that you will work with this afternoon. And of course, yeah, my first message, and this is just keeping with this buoy story that the buoy doesn't quite measure the spectrum, is that of course it's very easy to see the waves, and you can take any Google Earth image, beautiful waves, but measuring them is a bit more of a challenge. So I'll discuss a bit different techniques for wave measurements. I already talked about buoys, so I'll talk about satellite data and other things, and how the wave parameters measured from the spectra are derived. So the one specific thing about satellite measurements, and the most common of these, which is a satellite altimeter, is that these actually are the only wave data which are not derived from the spectra. So the way it works is essentially what the radar altimeter measures is the distribution of the elevation of the surface. So you imagine you have a satellite flying in space, and if the sea is flat, it's sending out a pulse, and so the like a spherical wave coming out of the radar antenna, and the spherical wave is hitting the sea surface, all right, and you get a bounce, and it's bouncing back to the satellite. So at time that corresponds to time before the radar pulse hits the surface, you have no echo at all, so you get nothing. So if you look at the time series of the radar return, it's near zero. It's a thermal noise. So you have no echo from the surface, and then at some point the radar pulse touches the sea surface, and you starts having some echoes, and in the what the radar is listening to, you get a spike, and the return goes up very fast, and then this region which is scattering back energy to the radar expands and gets this annulus shape, and then the returns slowly decrease because the radar beam is not very wide, so you have a narrow beam of a few degrees aperture, and so you only get echoes from this beam, and as a result, the returns go down. And the shape of this curve here is what is called a waveform of the altimeter. This is for a flat sea surface. Now, if you have a sea surface which is not flat and rough, instead of having this very simple return here, you'll get some return from the crest of the waves initially, and then the mid-level, and then at the end you get the return from the trough, okay, at this stage. So instead of having a very sharp increase of the return, you get something that is smoother. And so the shape of this waveform, essentially the distribution in time of the return of the radar is actually the PDF of the sea surface elevation. So what you're measuring with the radar altimeter is not the wave height from the spectrum, but you're measuring the wave height by the distribution of the returns. And in theory, the sea surface is Gaussian, and you have a theoretical shape of this waveform, and from that you can fit some parameters and estimate the wave height. Okay, so this is the only case in our typical measurement in which we don't use the spectrum. We directly have the distribution of the wave height, and from that you get the significant wave height. And of course, the mean level gives you the mean sea level. So most of the altimeters were actually launched in place to measure the mean sea level. But as you can see, if you had a flat sea surface, you would have an accuracy on the mean sea level of only 40 centimeters, because the time resolution of this waveform corresponds to a return time of the radar pulse of a few nanoseconds, and that's a 40 centimeter gate in the vertical. And so each dot on this curve corresponds to 40 centimeter range on the vertical. That's 40 centimeters for JSON, TOPEX, and so forth. The new Ka band altimeters, which is called LTK or SARAL, was launched last year, has a 25, I think, centimeter range resolution. So LTK is able to measure smaller wave height, because yes, with 40 centimeter, essentially you cannot make the difference between a 20 centimeter wave and 30 centimeter waves wave height, because it's the waveforms are essentially the same. You don't have enough resolution if the waves are too small. So the altimeter works really well for big waves, It actually seems to be working all the way to more than 20 meters significant wave height. And of course, we don't have any other measurements to validate beyond 15 meters. So, the altimeter for the big waves works really well. For the small waves, below 1 meter, it can be a problem. The other important thing is that the altimeter measures over an area which is a footprint of the radar, and it's typically like 7 kilometer diameter. All right. And the other thing is, well, I'll show you. Yeah, it can be pretty noisy. So the raw data from the altimeters is this waveform, and typically is measured 20 or 40 times per second. It's what people call the 20 hertz data or the 40 hertz data. Most of the people never look at that data. They only look at the 1 hertz data when everything is averaged, and you get an average of the wave height every 1 second. Okay. You can actually go back to the 20 hertz data and do some really funny stuff. Like this is an example. This is optical imagery, and this is the estimation of the radar map backscatter from, I think it was LASON. And you can actually reconstruct the map of the atoll here in the Pacific coral reef by mapping out the waveform to the surface. Yeah. The typical coverage you get over 1 day is something like that, and that's almost since 1993 when it was ERS-1 was launched, and very soon after it was TOPEX Poseidon. So here, this is a map from January 1st, 2009, and you can see the tracks of the altimeter. So it's it's following an orbit. It's going down, or rather, the Earth is turning and the satellite is going in a near polar orbit. All right. Some satellites like LASON and TOPEX were limited to 60-something north, so it was cutting through Norway. The Norwegians were very upset about it. Some other satellites go further north and south. So in the south, it's not a problem because 66 you only have ice shelves. But in the north, the tracks here are from ERS, Envisat, and SARAL. And these are the European Space Agency missions. They go further north. All right, and the colors here are the wave heights from the typical day. So it goes up to 12 meters in here in red. Of course, wave height can be bigger, and the altitude works pretty well with that. So when you see this, you see you have gaps, right? So if you're not lucky, you have a big storm here, you're missing it. And yeah, if you're doing studies of a small region of the ocean, the altimeter is mostly useful because it's interesting to validate the wave model that you're looking at. So if you're looking at the Aegean Sea, for example, or the Western Mediterranean, there's going to be actually quite a few altimeter tracks there. And even if it's not available every day, you can compare on the days you have the altimeter your model and check that the model is doing a reasonable job. That's one of the, I think, most powerful uses of the altimeter data. Of course, now we have more than 20 years of data, so you can start doing statistics on the extremes, long terms, and even in small regions like the Bay of Biscay or something like that, you will have enough data to say something about the extremes of the wave height. There's a few issues with altimeter, as I was saying, yeah, below 1 meter, because you don't have the resolution in time of a few nanoseconds. It's related to resolution in vertical. So the small waves, you don't discriminate them very well. Close to the shore, you have issues that get echoes from the land, like mountains in the land that can come together with the echo from the ocean, and that can corrupt things quite a bit. And so it depends if the land is flat, close to the ocean, or if you have mountains. But typically, within 20 kilometers from the shore, you have some problems. And as I said, yeah, it did look good up to 20-some meters. We had a paper about that a couple of years ago. But we have very few validation above 12 meters. So we don't know how accurate it is. It seems to be good up to 20 meters. Wave height, significant wave height. The data is actually improving with the newest satellite missions. SARAL LTK, we had a publication about that, came out this year. It actually has more accurate data than TOPEX or LASON or ERS. But the problem we have is that from one satellite mission to the other, or even during the lifetime of satellite mission, data can drift a bit, or sometimes they do some reprocessing to improve sea level, but because they don't care about the wave height, You can get an error of 20 centimeters of the wave height just because it didn't care about it. The problem with this, of the wave data from the space missions is that nobody cares about it, except for very few people, and Pierre Kesselou at IFRAMER here is one of them. And so he spent his life trying to put all the satellites together to have them agree, not only on the wave height, but yeah, one thing I didn't mention is that satellite also measures the backscatter from the sea surface, so the amount of power coming from the surface. And this backscatter is related to a funny variable which is called the mean square slope, or the variance of the slopes. And that is related to some high frequency part of the wave spectrum. So we're not only measuring the wave height, we're also measuring this mean square slope. And some people are using this mean square slope to estimate the wind, but it's really the mean square slope. All right. And so this is where we have some calibrated databases. So there's one at IFRAMER. We have some Australian colleagues that have their own calibrated database of all the altimeter data. You can go to the IFRAMER website to get all the data in NetCDF, which is clean and nice and all put together. And that was done through the GlobeWave project. But if you're looking at 1 Hertz data, so 1 point every 7 kilometers or so, this is an example of a track around Hawaii. So this is a model results from WaveWatch. And this is a track here, and you have here the wave heights the function of the latitude. So this is south, this is north. And you see the satellite is flying from south to north. So here it's giving you the proper trend. So the satellite is the noisy stuff in black, and the model is in red. So you can see the wave height here. This is between the 2 islands. So even if it's narrow region with JSON, you can get something interesting. And here above that. But you can see that at 1 Hertz every 7 kilometers, it is very noisy. The noise is about more or less 10% or something like that. And that's life. This is because in the footprint of the radar, there are not so many waves. And so when you're doing some average wave height, there's always some error bar around it. And you have to be aware of that. It's a bit less noisy with SARAL, but still the noise of the order of 10%. Okay, so that was about the altimeter and the satellite. And now the other type of measurements, which are all coming from the spectrum. So as I told you, we have this 2D spectrum. You can integrate in direction to get a 1D spectrum. And of course, when I was integrating to get the total energy, I was integrating from 0 to infinity, and you never have from 0 to infinity in reality. There's always some spectral boundaries, a minimum frequency and a maximum frequency. You know, the shortest wave you would have on the surface are around 10 Hertz. We never go that far usually. And so you have to be careful that when you're comparing the model to the measurements, or you're interpreting your data, you have to bear that in mind. And that is especially true for parameters that are sensitive to the high frequency, and I'll tell you what that is exactly. The mean here, the TMO2, is sensitive to the high frequency partial spectrum. And what I said before is we have very few measurements of the full 2-dimensional spectrum. And when I say very few, that's really very few, just a couple field experiments. There's no routine measurements of the 2D spectrum, except, well, maybe you have a few arrays here and there. So the SRF array in the US of Duck, North Carolina. There used to be an array in the California coast. There's a couple gauges in the Adriatic. There's one platform in the North Sea with 4 lasers, but 4 is only, you know, not many spectral resolution and so forth. So the first parameter that we usually work with is a significant wave height. And the way we define it from the spectrum is this. So if you have the spectrum, so here it's written with an F. Yeah, people put an F or an E, it's the same thing. It's a directional frequency spectrum. If you sum the spectrum over frequencies and direction, you get the total sea surface variant in meters squared. All right. And if you take the square root of that, you get a weight scale of the height. And in practice, we take 4 times the square root to define the significant wave height. And this is, you know, when people are talking about sea states, it's usually the most important parameter. Of course, you have this integration from 0 to infinity. And another warning here that in some cases, for example, if you have a pressure gauge at the bottom, you typically are measuring only one part of the frequency spectrum and not everything. If you're using SAR data, only measuring the swell, you have to be careful also that don't get the full wave height, or yeah, well, there's some algorithm to get a full wave height from the SAR, but yeah, you have to be careful about all that. And as I was telling you, yeah, the sources of data for that. So the altimeters is one way to estimate the wave height. You can measure that with buoys, ADTPs, and models. And typically at ocean scales, the errors on wave height from the model or from the satellite will be around 10%. In coastal areas, it can be much more than that. It depends where you are. And these errors in the models will change with the forcing, the physical parameterizations, and the numerical schemes. So the forcing, this is independent of the wave model you are using. The physical parameterization is somewhat dependent on the wave model. There's some more or less some parameterization you can find in different models, but not all of them exist in all the models. And then the numerical schemes and the method of resolution is really model dependent. And some models like WaveWatch actually has different options for the numerical schemes. We'll talk about that in more detail tomorrow. And to give you an idea of using different models, this is actually both runs are from WaveWatch, I think. So it's the same computer code, but I used a different parameterization from the wind input and dissipation. So the algorithm that tells you how much energy is given by the wind or given or lost by dissipation. And here you have the map of the normalized root mean square error for the wave height compared to the altimeter. 1 year of data with all the altimeters together. And it goes from large errors in red, and that's above 20% is all red typically. And the low errors is in gray, like around here, and the trade winds is around 5%. So the average error for the entire year. So, in some cases, in most places, this parameterization is better than this one. But still, there are a few places where this one is a bit better. If you look carefully, you will find that here, for example, in Southern Ocean, it's green, which is around 10%, and here it's more blue, which is around 8%. So it's not like one parameterization will work everywhere better, but they have different behaviors depending on how much swell and wind sea you have. You have more short waves or long waves coming from far away. Still, if you're happy with 15% error, both parameterization will give you the same result. And the very important thing is that these two model runs actually use the same wind forcing. So the wind forcing is the most important thing in a wave model. If you don't have a good wind, then you're going to get garbage at the end. And in regions like here, the currents also are very important. So forcing is very important. That was about the wave heights. The next most important parameter that are derived from the spectrum are related to some frequency estimates. And the most common of these, which I don't like, but people use it a lot, is a peak frequency. And by definition, the peak frequency, and I should have a plot somewhere. No, I don't have a plot of the spectrum. That's too bad. Okay, let's go back to the peak frequency is the frequency at which you have the maximum of the spectrum. Okay, I had a spectrum somewhere. So make things very clear. All right, so I have this spectrum, for example. So in this case, in that spectrum, the maximum is this one here, okay? And if you look at the frequency of that maximum, blah, 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 you're going to end up with 0.08. That's the peak frequency. All right. Very simple. The problem of this very simple definition, oh yeah, I had plenty of spectrum after that, is that it can be very noisy because you have different peaks in the spectrum. In that case, you had gravity waves, but sometimes you have swell or different swells and the wind sea. And if the swell becomes higher than the wind sea, the peak frequency will jump from one peak to another. All right. So it is noisy because of that. It of course depends a lot or quite a bit on the spectral resolution. So if you have a spectrum which is coarse, another which is finer, you get something different. And that effect of discretization, because of that, instead of just picking the discrete frequency at which the spectrum is maximum, what is done in WaveWatch is that there is a parabola which is fitted to the peak of the spectrum, and so that gives a slightly continuous definition of the peak frequency as a function of the shape of the spectrum. Now, another alternative to the peak frequency is to use a mean period. And then, well, you have different flavors of the mean periods. You can define a general mean period like this. So the TMOP is some integration of the spectrum. So we have the spectrum here in frequency times the frequency to some power p. Okay, so you sum that up. And if you divide that by the integration of the spectrum, you will get something which is proportional to the or has the same units as the frequency to the power p. So if you want to go back from this to a period, you have to take the power -1 divided by p, something which is going to be 1 over the frequency, which is a period. All right. So depending on what the value of p, you get different definitions. So if you take TMO -1, which is weighted by the frequency to the power -1, as you can understand, it will give more weight to the low frequency. Okay. If f is small, if you take it to the power -1, it's going to make it bigger. So it puts more weight on the low frequency, and this weighting actually happens to be the same as the group velocity in deep water. And so people that are looking at the energy flux for marine energy things, they usually like to work with the TMO -1 because it is a proper period to define the energy flux, for example. Okay. Actually, for a lot of coastal applications in which you're looking at maximum water levels, which may include gravity waves or other things, TMO -1 is also a very good indicator of the maximum water levels, and that comes into the extreme run-up on the beach. Usually it's more related to the TMO -1 than it is to a TMO2, for example. Now, for other applications in which you're interested on the sea surface velocities, like you have a pile on the platform, and you want to look at the power or the forces exerted by the waves on your pile or structures, and that's using Morrison's law, for example. This is related to the orbital velocities. And because the orbital velocity is the amplitude times the frequency, the spectrum of orbital velocities is the spectrum times the frequency squared. And so this is why this TMO2 with the frequency squared times the spectrum is giving more weight to high frequencies. This TMO2 is more convenient when you're looking at forces on a structure. If you're looking at other things like the Stokes drift, which is the spectrum actually weighted by f times k, in deep water that's going to be f to the power 3, then you're going to look at the TMO3 and so on. TMO4 would be something related to the vertical acceleration or the mean square slope. In practice, TMO2 is actually very close to the zero crossing period, which is used by people that do wave-by-wave analysis. And that was shown by Longet-Higgins in 1960s, a couple of papers about extremes of surface like that. So you can actually show that for a narrow spectrum, the TMO2 is the same as TZ. But as I said, it's sensitive to the high frequency tail and the F max that you put in there, because you're giving more weight to the high frequencies by multiplying it to f to the power 2. Then the range of frequencies is important. And in practice, you will see that with the ST4 parameterization, which is one of the flavors of WaveWatch that you will be running tomorrow, the TMO2 can be more accurate than with ST3, for example. ST3 is a parameterization from Janssen et al., and ST4 is my parameterization that was developed a couple years ago. TMO1 is closer to the peak period, so it's lower frequencies, but it's not the same as the peak period. And of course, if you want to compute things like the bottom velocities, where you will find many papers in literature that tell you, well, maybe you should use TMO -1 or blah, blah, blah. But in practice, it's never as good as applying the proper transfer function that I talked about before and computing the integration of the full spectrum times the transfer function to get the orbital velocities at the bottom. All right, so these are a couple examples of this funny mean square slope behavior, which essentially is telling you how the tail of your spectrum is behaving, because it's the spectrum times the frequency to the power 4. And this mean square slope and there's a G missing something here because otherwise it's not non-dimensional. So I think this should be divided by G squared. Right. So you take this divided by G squared, you get a mean squared slope, and this mean squared slope happens to be a function of the wind speed and the wave age. And oh yeah, no, here's not the mean squared slope, it's the Stokes drift. All right, sorry. So this is a Stokes drift. So the drift due to the wave motion at the surface of the ocean. So Stokes drift divided by the wind speed. And so you see that it's around 1.5% of the wind speed. And these are coming from model results. And it as a function of the wind speed, and the different colors is a function of the wave height. And this is to illustrate to you that two different wave models can give you two fairly different solutions. I mean, on average, it's around 1 to 1.5%. So the average is about the same. But in this parameterization, if you go from wave heights of 2 meters all the way to 9 meters, you're going to have an almost doubling of the Stokes drift. And in that parameterization, you get something which is increases only by 30%. The reason for that is that people that developed this parameterization, they didn't care at all about the Stokes drift. They never looked at the shape of the signal spectrum. And we tried to do better 10 years later. So we managed to do something better. Actually, this fits pretty well to the observations. There's still issues with the tail, so we're still trying to fix the tail. So it's not a solved problem, especially because we also want to get the proper wind stress from the wave. So different models with different parameterization can give you very different results for these parameters. The wave height is almost the same because the models are tuned to get the right wave height. But for other things, you have to be careful. That's for mean square slopes. About the directions, how we define the directions from the spectrum. So as I was telling you, even the buoy doesn't measure the full spectrum. So usually we work with a mean direction as a function of frequency. And so one way to do is to define these moments, A and B. And this is just a projection on the X and Y axis of the spectrum. So you take the spectrum times cosine and spectrum times sine, and you take the arctangent of these two quantities, you get the mean direction for the. So that's for the entire spectrum. But you can also do that frequency by frequency, and then you will get the mean direction for each frequency. A small warning here. It is possible that there is actually no way to propagate in the mean direction. Right? If you have swell from the east and windy from the west, you can get a mean direction from the north. There's nothing is coming from the north. So again, if you're designing a harbor on a small island and you're looking at wave direction statistics, mean parameters can be very dangerous to work with because you're going to design a harbor and you're saying that the wave is coming from the north, so you need to shelter from the north. There's not something coming there. So mean parameters is always a bit tough. Okay, that was the mean direction. This is directional spreading. Again, from A and B, you can define this thing, and that will be directional spreading. And the way it's defined, if you have a narrow spectrum, which is Gaussian, this sigma will actually be the sigma of the Gaussian of that narrow spectrum. And by definition, spreading goes from 0 to 81 degrees, and 81 corresponds to the case in which you have equal energy in opposite directions. And one small warning about this is that, not so many people look at the spreading. It's a very interesting parameter, though. And the big buoys have some bias on the spread, especially the 6-meter NOBAD buoys or the 3-meter discus buoys from the NDBC. The data wells usually are pretty good for directional spreading. And something we played a bit with in the last years is that if you have reflection from the coastline, it may not change much the wave height, but it can have a big impact on the directional spreading. And we've actually used this to validate our coastal reflections. Now, the mean parameters from the full spectrum, as I was telling you, especially for the direction, is not always meaningful. And so another approach that has been used quite a bit by marine forecasters is to chop up the spectrum into what's called partitions. The basic idea is that, in general, you will have several well-identified trains of waves, so some swell coming from one direction at a given frequency, another swell from another direction. And in order to be able to summarize that information with just a few numbers, it's very convenient to define regions of the spectrum that correspond to these swell partitions. In practice, the way it's done in WaveWatch is it's called the inverse watershed algorithm. So essentially, you detect the peaks, and it's like you take the spectrum image into dimension, you flip it upside down, and you pour some water into these holes. And as long as the water stays in the basin is the same peak, right? That's making sense, but like a watershed in a terrain on land. So basically, one peak has a partition attached to it. And sometimes if the data for model, it's easy. For data which are noisy, it's more problematic. You have sometimes many peaks, so you have to do some smoothing to get the partitions to work well. But this is a nice way to separate one swell from another swell, and here at Haiphong you get the wind peak. Right, and that's a typical example of a spectrum in the Pacific, in which you have, okay, so here the 1D spectrum, so we have one big peak, another peak here, and this kind of shoulder here. And if you make a 2D spectrum from the buoy data, you get this peak here. 2 is this one. And this is number 1, and number 3 is this. And actually, this is a swell. This is a wind sea. They're very close. So here, it's almost like a continuation. But if you actually do the watershed business, you actually can separate these two things into different peaks. And then you can summarize all that by some parameters. So the first swell actually is this one. It has a wave height of 2 meters, a peak period of 11 seconds, and direction of 55 degrees. And the second swell, which is this very big peak, but it's more narrow, so actually there is less energy, because the energy is the area under the curve. Okay, so because it's higher but narrower, the energy is smaller, and the wave height, with the square root of the energy, is only 1.7 meters. Peak period is longer; it's lower frequencies. All right, and direction here is very different, coming from 310. So in that case, it was this is north of Hawaii. So this number 2 is coming from a storm, which is north of Japan, and this one is from a storm in the Gulf of Alaska. Right. So when you know the situation on the globe, you can tell, okay, this swell is coming from that storm, and that's a typical situation in which long period waves can travel very far away, especially in the ocean, and the short period waves usually, they decay in a few thousands of kilometers. So you usually have short waves only from the local wind, more or less. Of course, in the Mediterranean, you can have some swell. You can have some swell from Sardinia coming to the French coast, or the other way around, but usually it doesn't last very long. It's very short swell. If you have a small ocean basin, you're less likely to have swell coming from far away, and it usually is only local winds. If you go inside of the Bay of Brest, it's mostly local winds, not swell. The entrance of the bay here is very narrow, so you have almost no swell going into the bay. So that was the idea of the partition, and so WaveWatch has been designed to, there's a lot of output for doing this partition. You can have all the partitions you want in separate files, or have maps of different partitions, and I think we'll be looking at some of that. We'll see. If you have some questions about partitions, ask Mikael, and we can do some special tutorials for you that maybe otherwise we don't do during the week. Again, the bottom parameters, this is how you can define the RMS amplitude of the bottom displacement. So if you imagine the water particles on the bottom, they go back and forth with the waves, back and forth. And you can define the displacement, like the wave height, but horizontally. And the displacement is only half of it's like the radius, not the diameter, okay? And this is the velocity that corresponds to that. And again, this is the RMS velocity, or more exactly, the RMS amplitude of the bottom velocity. So you have to remember that our waves are random to get big waves, small waves, big waves, small waves. Okay, so you have to be very careful about how you define the parameters. Some parameters are just the RMS values, some others are the RMS amplitudes, and then you have the significant values. So the significant wave height is 4 times the square root of the variance. Okay, if you took only the RMS wave height, it's a factor square root of 2 smaller than that, so it would be square root of 8 times the variance. And here, this would correspond to the RMS wave height. So if you want to have the significant bottom velocity, you have to multiply that by square root of 2. And the maps, for example, that we produce on the Prévimère website, they use a significant velocity, which is square root of 2 times this. right? So when you're going through threshold of sediment motion, all that stuff, you have to be careful about what's RMS, what's amplitude, what's everything. If you're only caring about the wave heights, don't worry too much about it because people always talk about the wave heights. But for the orbital velocities, and yeah, be careful. Okay, yeah, this is the example of the Stoke-Drift. I was showing you a bit before. So that's the how you can define the surface Stoke-Drift from linear theory. Spectrum times f times k. So this is a vector, and it's a wave number vector, and that's a typical distribution of the Stoke-Drift as a function of wind speed and wave height. This is from buoy data. Yeah, some other parameters which is defined from the spectrum. This is the radiation stresses. So that's going to be very important when you're coupling waves and currents. It's essentially the push that is given by the waves to your currents. So how much the waves are pushing the current is coming from the divergence of this radiation stress. And so this thing is actually a tensor. So it has 4 components. So it's S, X, 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 Y, S, Y, Y, and X, Y, X. It's symmetric, so you only need 3 because the S, Y, X is equal to S, X, Y. And you can define it from the spectrum by this, spectrum integrated by this. And in here, N is the ratio of the group speed and the phase speed. And typically, this is what you would situation would have. So if you have waves coming from the left to the right on the bottom, and in that case there is no braking. So here the wave momentum flux is increasing from here to there, and as a result the balance will be with a set down, so the sea level is going down. If you have braking, it will be the other way around. Usually you have as a wave break, the momentum flux reduces, and so that's pushing the water. You really get some current and all that stuff. So in WaveWatch, we're computing these things. We're also computing parameters that are useful for coupling to the currents, and this is what is called the Bernoulli head, and I'll talk more about that on Wednesday. And the vortex force, which is some product of the wave-induced mass transport with the current vorticity. So what WaveWatch computes is also this transport and the surface Stoke-Drift, so that then if you multiply with the vorticity from your current, you can get the forces acting on the current. But don't worry too much about it now. This is just to tell you that you can compute this from the spectrum. And yeah, there's some nonlinear correction. This is for freak waves and whatever you want. And yeah, I forgot we had some seismologists with us. Okay, so there's one special slide for seismologists. As part of the nonlinear correction to the wave motion, there is a second order spectrum, and in theory, the nonlinear wave motion is acting like a pressure at the surface, which has a spectrum that can contain very long wavelengths. So a wave number almost 0, which means very long wavelengths, and a frequency Fs, which is 2 times the wave frequency. And so in theory, this is the pressure spectrum at K, at the wave number near 0. It's defined from the wave spectrum, and this funny directional integral here, which is this. This is a directional distribution. Essentially this is this M of F is E of F and theta divided by E of F. And so it contains the energy in one direction times the energy in the opposite direction. So it tells you how much energy you have in opposite directions. And so one of the output parameters of WaveWatch is called P2L. This is a second order pressure at wave number near 0. And if you run WaveWatch, then you can output this, which would be this thing here, and then you can actually try to reproduce the sources of seismic noise that are recorded on land, and that's it. What I want to mention here is that in practice, this integral here is very, very poorly known. So the model is likely to make a very big mistake on that. And actually, if you go from different parameterization, and so in WaveWatch, you will see is defined by these switches, ST1, ST2, ST3. If you go from ST2 to ST4, the result of this I of F changes by a factor 100. I do believe that we've made a lot of tests that it's better with ST4. It seems to be more realistic, at least up to frequency of 0.4 hertz. At high frequency for waves around 1 hertz, we don't know. So we have a student doing a PhD on this problem of the tail of the spectrum. and this directional distribution. But yeah, don't expect miracles for this thing at high frequencies with a wave model. And actually, even at lower frequencies, from some parameterization, it's actually very bad. And there's some papers about that. If you want to know, we can discuss that. All right, and I think that's all I had about this. Yeah, there's some other slides going to stuff online, but that's it. So any question about these wave parameters from the partitions, the mean periods, the mean directions,